Hi, this is Brian Nett with HowRadiologyWorks.com. Today we're going to talk about beam quality. This is a topic for X-ray imaging, radiography, and CT. So a little bit different from these type of beam quality issues, but what we're talking about has to do with radiography. So if you're a radiographer or if you're a radiologic technologist, think about hitting subscribe below and click on that little bell icon if you want to get notified when we release new content. So if you're interested, stick around, and beam quality is coming up now. This is going to be an overview of what we're going to talk about today. We're going to talk about issues in beam quality. First, what is beam quality? So we'll go to that first. So what is beam quality? We're going to talk first about what is beam quality. So beam quality describes the X-ray spectrum itself. So if we think about the X-ray spectrum, the X-rays coming out of our clinical X-ray tubes, they're not all one energy. That would be called monoenergetic or monochromatic, but they're a variety of energies. The highest energy is called the kVp, the kilovolt potential, and we have other videos where we talk about how the X-ray tube actually works itself, but here we're going to talk about just the beam quality issues, and X-rays are going to have different energies from the kVp all the way down to 0, potentially. And then if you look at this plot, the area under this plot is essentially showing how many X-rays we have in our X-ray spectrum. And if you look at one given energy, that energy is in keV. And if you go up, this will tell you how many photons you have at that energy. So that's what we're talking about. We're talking about beam quality. We're talking about measurements and effectively the information which is in our X-ray spectrum. Again, like I said, area under the curve here, a lot of times we'll talk about, that's essentially how many photons you have to make your image. So if we talk about it, a lot of times the terminology soft beam and harder beam are used, and those simply mean a soft beam has lower energy photons and a hard beam has more higher energy photons. So it's as simple as that. As your beam gets harder, it has more higher energy photons, its average energy is higher, and as your beam is softer, it has more lower energy photons. So that's what is beam quality. Next, why do we care about it? So as professionals in the radiography field, we really care about beam quality, mainly because of how it affects the image quality in our images. So in both CT and in X-ray images, these trade-offs apply. A softer beam that's a lower energy will give you a higher contrast. Again, we have separate videos about that, but a higher contrast comes because there's more of a difference between the attenuation coefficients of the different types of material in your image at a lower energy. So that's why we have better contrast at a lower energy beam. And this is especially true of things like iodine, bone, barium. Those things have big differences if you're going to lower energies. But higher kVp might be needed for your clinical imaging in scenarios that you need to get what's called the penetration, the ability for the X-rays to all pass through the object such that you can get a good exposure on your detector plane. Higher kVps can also have benefit in terms of artifact reduction, such as metal artifacts or photon starvation artifacts. Okay, so we said, what is beam quality? Why do we care about it? Now, what factors affect it? So first we'll just go over the factors that affect it in basic table form, then we'll go through some schematic pictures about that. But first and most obviously, the energy of the spectrum is determined most by the kVp. So that's something that's easy to change on the system, and the reason that it affects it is that if you're accelerating your electrons more between the cathode and the anode, they'll have more energy when they hit the anode, and thus they can generate X-rays that have more energy. So that's what you're doing when you're changing the kVp. The target material, if you change the target material itself, that's not something that's easy to do on the fly. So as a technologist, it's not something you'll be doing to your system. There's not a button typically that says target material and you change the actual target material of the anode. But just so you're aware, the target material does have an effect, and the heavier materials, the heavier metals, will actually attenuate the X-rays more. Additionally, pre-patient filtration. This is also a big one that you do often have control over, is the ability to insert pre-patient filtration. So this does lead to a harder beam when you have filtration in the beam itself, leads to a higher energy beam because those lower energy photons are preferentially attenuated by that pre-patient filter. So for instance, on a lot of systems, it's essentially, you can think of a thin sheet of metal that's being inserted, and that is attenuating those lower energy photons more than the higher energy photons. So beam quality. This is just a picture, the same as what we talked about in the definition beginning, but the kVp is the thing that's driving it here. Right here is a high kVp case, and this is a lower kVp case. And again, the highest energy is determined by the kVp that's selected on the system. So higher kVp will have a higher average energy, and lower kVp will have a lower average energy, with everything else being equal. So that's kVp. That's the biggest one, and that's one that you're selecting all the time on your system. And if we just look at the area under here, there's more area under this higher kVp, indicating that, again, all else being equal, you're going to have a much higher fluence, more photons at a higher kVp setting. That's why it helps with penetration. Beam quality as a function of MA. So I kind of give it away in the little title there, that is beam quality a function of MA? What we're talking about here is MA is only affecting the number of photons. It's not affecting the shape of this curve. It's just scaling this curve up and down, but not affecting the shape of this curve at all. So beam quality actually does not depend on the MA. But because we're changing the number of photons, we want to describe that as well. So instead of calling that beam quality, we'll call it beam quantity. So the number of photons that are under your spectrum. So here's two spectra. I drew them by hand, not terribly sophisticated drawing, so they might not be perfect. But the idea here is that the spectra should look the same. And the only difference is that the one with 200 MA has more X-ray photons underneath, but the average energy is the same because the shape of the spectra are the same. That's what we mean when we talk about beam quality as a function of the MA. Then, beam quantity as a function of kVp. This is one thing we talked about already. The kVp does in fact change the beam quality. Next, X-ray tube and target material. So again, does the target material affect the beam quality? You've seen this video or this little animation before. The idea is that the electrons come in, they interact, either via Bremsstrahlung or characteristic interaction, and then they come out of that material. And as they're coming out of that material, they're interacting with the anode material itself. They can be attenuated as they're coming out. And again, lower energy photons are going to be more attenuated. So if this material is more attenuating, it is going to lead to a spectrum with a higher average energy, because those lower energy photons are going to be more likely to be stopped in the anode. So next, impact of beam filtration. So beam filtration, like we talked about, is something you can insert. And beam filtration, if we look at an input beam, so imagine we have a spectra that looks like this, and that's what our input spectra looks like before we have the beam filter. And that beam filter could be tin, aluminum, and then after it's coming out, we can think about the input energy was here, the input average energy was right here. After the beam is filtered, it comes out, and then the filtered spectra might look something like this, where there's fewer photons because they were stopped in this material, and it has a higher average energy because the lower energy photons were more likely to be stopped inside of that material. So the main purpose of these type of filters is to reduce unnecessary radiation. So very low energy photons, for instance, are not going to be able to penetrate, and if they don't stand a chance of actually contributing to the image, then we consider that a wasted dose. So that's the reason why you would want to have some inherent filtration in your system itself. One thing that can help in that is the actual window of the X-ray tube itself, and then often you'll have additional filtration. We want to note that with this additional filtration, both the total flux is going down, but the average energy is going up of the X-ray spectrum after it comes out from a filter material. So we talked about what's the definition, why we care about it, and we talked about all these different factors that affect the beam quality. Finally, we want to talk about how can we measure it. So in the clinic, if we want to do quality measurements on the system, how can we measure the beam quality? So we can't take a detector, the detectors that we have to make the measurements that we use to measure our images, they typically measure all of the energies under this spectrum. So we can't just put our detector in there and say, okay, it looks like the beam quality is about good. We actually need a metric to measure the beam quality, and a direct measurement isn't really possible. It's very difficult to set up direct measurements of the X-ray beam quality. So instead of doing a direct measurement, we look for a surrogate measurement, something that's related to beam quality, so that as we change the beam quality, we want a metric which will change as well. And the surrogate metric which is often used is called the half value layer. So we'll define that in just a minute here. The half value layer is what's often used, and it's a surrogate measure. It's not a direct measure where we put a detector in and we measure the beam quality itself. We're measuring something that's related to the beam quality. So to measure the half value layer, we take, for instance, an ion chamber here. So we've talked about these before as well, where we irradiate the ion chamber. So our X-rays are coming in. Those X-rays are going to ionize the air inside of the ion chamber, and then those ionization events are going to be collected, and a signal, electric signal, is going to be generated. And so we get a measurement of an electric signal which is proportional to the X-ray fluence that's coming in. So we first do this without anything in the beam. Just measure with the ion chamber itself. This gives us our reference. So that's the exposure without the filter. That's a reference value there. Then we put in a little bit of beam filtration. So here's a little bit of beam filtration. Then we have what we call the exposure fraction. And that's going to be the exposure that we measure here, X-ray exposure we measure here, divided by that exposure without a filter. And then we get a point on this curve where we're plotting the thickness of material. So we put in one piece of material. So if this was 1 millimeter thick, we'd be at 1 millimeter down here. And then on this axis, we're plotting that measured fraction, the exposure fraction. Then we insert another piece of material, and then we can get another point on this curve. We insert another piece of material, we can get another point on this curve. Then the idea is we do a fit here, and we can see the relationship between the material thickness and between this exposure fraction. And then we want to know what's called the half value layer. So the definition of the half value layer is when the exposure is 1/2 of what it is without any material. So even if we don't have a measurement that's exactly at the half value layer, we can do a fit here to this curve. We draw a line at 1/2 here, and then the value for the 1/2 value layer is right here. So whatever this turns out to be on this axis, some number of millimeters of the given material. And if we do that, we characterize that in our system, we can track that over time, or we can compare different systems with that same measurement idea. So that's called the half value layer. We can talk about multiple half value layers. If you think about it, what we could do is if we took twice as much of that material, then instead of attenuating to where we get just half of the X-rays coming out, we could get 1/4 of the X-rays coming out. So if we had 2 half value layers, we'd get 1/4 of the X-rays coming out. If we had 3 half value layers, then we get a little more than 12% of the X-rays coming out, 1/8. And if you had 4 half value layers, you get 1/16, or about 6% here. So it's just 1/2 raised to the half value layer. That's the definition of how much exposure you're going to get coming out relative to the input exposure. That's a definition for the half value layer. And half value layer is indirectly measuring the beam quality, because if you have beams that have different spectra, those are going to be affected differently through these half value layer measurements. So in the case of the 80 kVp, the change in the half value layer, the change in the actual energy under here, in the case of 80 kVp, is going to be more dramatic than it will be in the case of the 140 kVp. So this is why we call it a surrogate or an indirect measure of the beam quality. So half value layer relationship with MA. We should know this because we talked about earlier the fact we know the beam quality doesn't depend on MA. So the half value layer shouldn't have a dependence on MA either. The idea is that the half value layer will be conserved after the MA is changed, because the shape of those spectrum is staying the same. So half value layer is not affected by a change in MA because it is measuring surrogate measure of the beam quality. So the overview. Coming again, we talked about what is beam quality, why do we care about it, what factors are affecting it, and how can we measure it. So this has been like a whirlwind tour of beam quality, and probably the most important thing here is really the why do we care about it section, because that affects the quality on the system, the ability to make images that have different contrasts or different amounts of penetration. But we do have interest in what factors affect it, so we know if we're changing the MA, we don't expect the beam quality to change. And we also want to know how we can measure it, so that if the system isn't acting as we expect, we will have a way to go and do some quality metrics on it. Thanks again. This has been Brian Nett with HowRadiologyWorks.com. Again, stop on over to the website if you're interested in more material about how radiology works.